Okay, guys, so continue with what we just talked about. I think I just made a mistake for this example. So all I need to do is to modify one part. So find the parametric equations for the tangent line to this function, to the curve of the intersection of this surface, and also this surface at this point here. Now, this problem here, as you can see that this actually it's a cylinder, right? So if we draw that apart, so if you draw this, so this is gonna be, you can see that it's a cylinder, right? And also z equals 4 minus x. So actually it is it's a plane. Okay, it's a plane. So those two, when you do this intersection here, a very bad drawing. Okay, guys. So I just want to let you see the brief idea. So they actually intersect with each other, and the intersection it actually generated a ellipse. Okay, so this is an ellipse. So the point 113, possibly it's some places here. Okay, some places here. And as you can see here, how do we figure out this equation for this tangent line? So briefly, we are looking for this tangent line here. Okay, to this point. Suppose this is the point P. Okay, 113 here. So as you can see here, the gradient for this cylinder, it's always normal, right? It is always normal. So if I can use a different color here, so as you can see, so it's always normal to here, and also the gradient for this surface is also normal. Actually, this is a plane. So it's actually, you can see that it's going to be the plane could be something like this. Okay. And then, so you can see those two gradient turns out if they do a cross product, and then realizing that the cross product will give you a vector, and that vector actually it's parallel to the to this tangent line. Okay, to this tangent line. So briefly speaking, we need to drive the gradient for both surfaces, and then we can ask a cross product, and then we can figure out the parallel vector for these tangent lines, and then we can drive these parametric equations for this tangent line. Okay, so that's kind of like the very, very brief introduction about how do we starting this process. So so back to here, if we denoted this function, denoted this corresponding function as this. So if I denote it, f x, y, and z equals x squared plus y squared minus 2 equals 0. Denote this is the first surface. And then g of x, y, and z denote the second surface. So we can denote it as z plus x minus 4 equals 0. Okay. So we can figure out, okay, what is the gradient for the first surface? Turns out it's a 2x, 2y, and 0, right? And also the gradient for the second surface is going to be 1, right? 0, and also 1 here. Both of them we need to evaluate at this given point, 113. So the evaluation at 1, 1, and 3 is going to be on 2, 2, and 0, right? And then the evaluation for the gradient of g at 1, 1, 3 itself, it's still 1, 0, 1. Okay. So after we got that, as you can see, what we need to do is we need to do a cross product. So cross, so it's I, J, K, you still remember that? So it's 2, 2, 0, 1, 0, 1. So it turns out, as you can see, you're going to have 2I, okay, and then for here, it's going to be minus 2J, okay, and then, so this part is going to be 0, so it's going to be minus 2K, okay. So that is this vector that is parallel to this tangent line vector. So the corresponding parametric equation for this tangent line is going to be xt equals 2t, right, plus 1. Yt is going to be negative 2t plus 1. Z of t is equal to negative 2t plus 3. Okay, so that will finish this problem. Okay, yeah. So that's how do we handle this? Okay, all right. So the next problem, I want to talk about one problem that is so given a surface f of xy equals xy minus x squared minus y squared minus 2x minus 2y plus 4, and I would like to figure out what is the is there a local maximum, local minimum, or saddle point? Okay. So talking about this pieces here, as you expect, I would like to maybe review the what we call the second derivative test first for the local extrema. So the second derivative test for local extreme, for local extremes. Okay, so basically what it says is if you have a function here, and of course the first and the second partial derivative, so the first and second, those are continuous at a point, so those are continuous. Okay. Throughout a disk and then centered at the given point, if we denote that point as A and B, and also this partial derivative, first partial derivative evaluated at this point A and B, and also the partial derivative with respect to y also evaluated this equal to 0. So in other words, this is a critical point. Okay, this is a critical point. And then, so if all this holds, then what we got is, the point AB is going to be a local mean if the second derivative evaluated at this point actually is greater than 0, and meanwhile, and the discriminant, which is here. So this is true. Okay, of course it's evaluated at this point. You're going to have a local mean. And then this point is going to be a local max if the second derivative evaluated at x is less than 0, and again the discriminant must greater than 0. Okay, again, all evaluated at this given point. The third one is this gonna be a saddle point if the discriminant is less than 0. Okay, it's less than 0. And then the fourth case here is no conclusion if this discriminant equals 0. Okay, in other words, if this situation happens here, and then this point we don't know whether it's local max, local mean, or saddle. So in other words, the second derivative test fails. Okay, we need to go back to search for other tests. Okay, so that is pretty much the second derivative test. So go back to the problem we would like to talk here, and you can see. First of all, we need to figure out what is the corresponding critical point. So that is, we need to figure out what is the partial derivative with respect to x. In this problem, it's y minus 2x, right? And then minus 2. Okay. And then the partial derivative with respect to y, we need to figure it out that it is x, right, minus 2y minus 2. Yeah. Maybe let's also figure out the mixed part, the second derivative, which is going to give us is negative 2. Partial y is also going to give us is negative 2. And also the mixed partial, let's see, is going to give us is 1. Okay. So the mixed partial, yeah, is both sides equals to 1. Okay, so this is good here. Okay, and now, first of all, we need to find the critical point. Okay, we need to find a critical point. That is, if you recall, if you want to use the second derivative test, the critical point, remember it's the partial derivative. It must be both equal 0, or at least one of them does not exist. Since the partial derivative for both exists here, so in other words, the critical point only exists when both of these equal 0. So in other words, with these pairs, that is exactly y minus 2x minus 2 equals 0 and x minus 2y minus 2 equals 0. We can actually solve these pairs of equation to figure out what is the corresponding critical point. Okay, critical point. So it turns out that you can solve this. Let's see. So if you multiply, if this is 1, this is 2. So let's see, if you use 1 times 2, you're going to have 2y minus 4x minus 4 equals 0, right? So if you denote this is equation 3. And if we let 2 and 3 adding together, why we do that? Because we have 2y here, we have minus 2y. And turns out you have, let's see, 2y minus 2y gone, so it's negative 3x minus 6 equals 0. So turns out that you can solve x equals negative 2. So you have x equals negative 2, you plug into here, and so it's y minus negative 2 times negative 2 becomes into 4, plus 4 minus 2. So it's y plus 2 equals 0. Turns out you can also solve that y is equal to negative 2. So the critical point we have here is going to be negative 2 and negative 2. Okay. So this is the only candidate to become either it's a local max, local mean, or saddle. Okay, but we don't know at this moment yet. But let's try to figure it out. First of all, it turns out that if you remember the discriminant, in this problem, it's going to be minus 2 times minus 2 minus 1 squared. So it's a 4 minus 1 is 3. It's greater than 0. So this discriminant is greater than 0. That guarantees that this critical point is going to be either is a local max or local min. Okay. So this is just a part of the condition. Whether it's a local max or local min, we need to apply the sign, right, or determine the sign of the second derivative with respect to x. So f partial x is equal to negative 2 is less than 0, right? It's less than 0. So if it's less than 0, recall, let me bring this page here, our second derivative test, you will see that actually it belongs to this category, right? Because, again, second derivative is less than 0. Discriminant is greater than 0, so it's going to be a local max. So we can see that at this point, negative 2, you have a local max. Okay, you have a local max. So yeah, so this is the explanation of this problem. So hope you like it, and thank you.